So today our plan is we will talk something about some of the graph parameters. So for some time we will be away from algebra. Okay. So have you guys heard about coloring problems in graph theory? So this coloring is a problem which arose sometime in 1700s, where when cartographers, when they started the problem of coloring a map. Okay, so given a map, they wanted to color maps, like political map, so that you distinguish between two adjacent states. Okay, so this is the first part of coloring problem that arose, and in continuation to this we have the other variations of coloring problem. So today we will try to touch upon three of the variations. Okay. The first one will be the vertex coloring problem. Okay. So what do you mean by vertex coloring? I mean, what does the term reveal to you? You just want to color the vertices, right? That is in simple terms, right? So given a graph G, and so a graph has set of vertices and set of edges, of course. So our idea is we are also given set of colors. Okay. So for time being we will I say colors, but I will be using numbers. Okay, so that is quite easy to deal with. So suppose I am given say k colors. Okay. Can I color the graph using these k colors? So this is one of the decision problems, and vertex coloring problem also has its other variations. So the first question is, so given colors, can I color the vertices of the graph? So how many colors you need to color if you start trivially? To all the vertices, I did not give any condition, right? I just asked you to color the vertices. So you can use one color to color all the vertices, right? That is a big possibility. Or every vertex you can give a different color. That is also another possibility, right? So then what is that we are interested here? I mean, both the ends are possible. If I color with every vertex with same color, then what are we doing actually? If I color every vertex of the graph by one single color, I mean, does that give you some information? See, ultimately we are trying to do coloring, so that means we are going to attach some real world problem to it, and we want to see how we can handle it, right? So by using just one color, I am not distinguishing anything here, right? So the idea is there should be some place where we can distinguish our graph and the vertices and the edges, everything, right? So this is where the idea of proper coloring comes, okay, or in general in some books they call it as just vertex coloring itself, okay, or proper coloring. So the idea of proper coloring is that given a set of colors, okay, and this vertex set, how many colors do I need to color them so that any two vertices, if they are adjacent, they should not receive the same color. Okay, so this is a proper coloring. So to define, given graph G and say some colors k is there, we want to color the graph, color the vertices. So by coloring, what we mean? We want to assign the colors to the vertices. Okay, so color the vertices such that no two adjacent vertices get same color. So by gets or receive, we use different terminology in different context. Okay. So mathematically, if we want to define this, it is nothing but you find a function, okay, from the set of vertices to the set of colors. Okay, so every vertex you assign it a color so that you map it to a particular color. Okay. So mathematically we will call it as like from V to color class or a color set, whatever we have, say suppose C is this color set, then I want to find a mapping F from V to C such that F of V1 is not going to be equal to F of V2 if V1, V2 is an edge, if it belongs to an edge, right. So if with this condition, how many colors do I need? Suppose a graph on n vertices, if we are talking about. So here there is one trivial case that I can color every vertex with different colors, right. This is the other extreme case, right. So now in this case, if you see, it is again like it's always a possibility, right, but we don't want this. We may be overusing resources in case. So the question now, the decision problem or optimization problem here is to find the minimum number of colors that is required for a given graph on n vertices. With how many colors can we do it in minimum? That is a minimum possibility, right. So this is our question. So to find a minimum color class set, so minimum set of colors, right. So this is what we have been like, you already know this concept, so now we will go a bit faster now. So can we go for some special classes? What about a complete graph? How many colors do they require? N colors, right. And what about bipartite graphs? 2 colors. How about cycles? Even cycle 2 colors and odd cycles 3 colors, right. So what is the connection between all these 3 class of graphs? I have been talking about special class. So complete graph Kn or the cycle graph Cn or any bipartite graph, right. This also we have been talking about. So each of them have some connection. Say here, say first let me talk about Cn n even case, right. So what is the connection between all these 3 classes and the colors that you are saying? Is there any relation that it is connecting? I mean, it could be connected using when n is even. Of course, I put it separately because we have an odd case coming out of it, so we need to talk about it, right. So what is that connects all these 3? So you gave me also the answer, the number of colors required for Cn is n, this is 2, this is also 2. Of course, I think it may not be relevant to talk about bipartite graphs, but what about these 2 other classes? Yes. So we can also see that every color forms an equivalence class, okay. So each of the color partitions your given graph into color classes, right. This is another way of looking at the same thing. Say when we say bipartite, this is also there in our mind, right. So every color, when we say we are coloring a graph, a proper coloring, we are ultimately ending up in an independent site, right. Every vertex with same color will receive the will be nothing but an independent set, right, that set, the set of all vertices. So here again, each of the vertices, they have, I mean, each of the color that is being colored will partition your vertex set into different classes, right. So these we call it as color classes. And apart from that, anything else can you connect? Okay. So think about it. By the time I will put one more question. Can you give me a 4 coloring of this? Is it difficult? That is the idea. That's why I asked this question. I am not getting any answers, right. So one way is you can just color each vertex with 1 color, because there are only 4 vertices here, right. What about a 3 coloring? So there is a possibility, right. So 1, this could be 2, 3, 2 again, right. 2 is only free vertex that we can do it here. What about 2? 2 is not possible, right. Why? There is a triangle present, right. So we need at least 3 colors to color them differently, all the 3 colors, right. So that is what we are trying to capture in from the above part also. So what is that common now? Okay, not necessarily, I can start anywhere else. Say suppose I just want to color this with 1, it does not matter, No, I am asking now the connection between what is there on top and how we colored here and what you came up with. There is something that is common between all these things. Can you see what is that? Highest degree. Is it degree n minus 1? So why you use color n? Yeah. And bipartite graph, I did not tell you what degree it is. I can have maximum possible bipartite graph there. Here you people could say something so relevant to that, so in connection to that I will go. So here you said this is 1, 2, 3 and 2. So what is this triangle telling you here? Odd cycles. Okay, we will go into C and then you have started odd cycle. What about C and N odd? How many colors you require? 2 colors. K color? 3 colors. Then everybody are convinced there, right? So that you need 3 colors. So my first question was about the previous ones in the black. What is it that is connecting these two? Number of triangles. Any other answers? Okay, maybe I will give you one more example. What about this? You can do by 2 colors, right? So number of triangles, as you say, if you say it's 0 then. So does that ring you a bell? Anything here? From morning sir is talking about this one class since morning. Okay, I will break it up for you guys. And we have in fact one important class here, which is the complete graph. You know you require n colors, that is the minimum possible, right, because every vertex is going to be adjacent to every other vertex, right. So this is a global property. If I reduce this to a given graph, okay, to a subgraph of it, okay, if this similar property holds, then we can talk about it there also, right. So in each of this class, what we are trying to see is a maximal subgraph which is a complete graph, a subgraph which is complete in itself, that is it has when we say complete, its induced subgraph is complete, right. So if you look at this one k4 minus e that we have taken, the complete graph here is nothing but, what is a maximal complete subgraph? By maximal complete subgraph, what we mean is, given the graph G, I need to find a subgraph H such that H is going to be complete, right, complete on whatever vertices H is defined on, right. So in this example, if you see 1, 2, 3, 4, on 4 vertices that we have drawn, what is the complete subgraph that we have? Maximal complete subgraph on 3 vertices, right? Only on 3 vertices we have. Whereas if you see the other graphs that I have drawn here, either CN or bipartite graphs, they all have, what is the maximal subgraph? 2, right? If you add any third vertex, it is not going to form a triangle obviously, right? So in each of these graphs, the maximal subgraph has size 2 in the other CN and bipartite graphs. So the color class we expect it to be, we require at least 2, right? There is a maximal subgraph which is complete, so we need at least that many colors, right? That is the idea here, right? Whereas in CN, when n is odd case, it is kind of an what do we call special case. We always have some exceptions here and there, right. So n odd case is a very special case. So and similarly we can also talk about Kn also here. Okay. Putting this in formal terminologies, we call that a graph with the number of colors, the minimum number of colors that is required is called as a chromatic number, right, or and we denote it by chi of G, right. And the one that we are talking about, the maximal connected subgraph, right, the maximally connected or maximal complete subgraph that we are looking for, it is nothing but we are looking for a click in a graph, right. A click is nothing but maximal complete subgraph, right. And the corresponding number to this, if there is a maximal complete subgraph, a click sitting inside a graph, then we call the graph has a click number, and the click number is going to be nothing but the number of vertices of the subgraph, right. And we denote it by omega of g. Okay. So, the idea here is, if you see any graph requires at least omega of g colors, right. So, this is at least, I think this should be clear, omega of g requires at least, I mean chi of g is going to be at least omega of g colors, right, given any graph, because there is a subgraph which is complete. So, we need to color at all those vertices with different colors. So, we need at least those many colors, right. So, can we color by exactly that colors? Is it also equal to? Already we have seen some example here, right. See n odd case, right. You do not require, I mean you cannot do it with 2 colors, but you need 1 more color. So, can I say that chi of g will be less than or equal to omega plus 1 at least? Either omega or omega plus 1, can I say that? So, here we will go into the next thing. Next question is, given omega equal to 2 and I give you some integer k, now think of a graph whose chromatic number is k and click number is 2. Is it possible? Can you construct a graph, or is it not at all possible? Any integer k. So, my question was, give me a graph whose omega is 2, that is click number is 2 and chromatic number is k, for any k. So, obviously we know if omega is 2, at least for k equal to 2 we have a class of graphs, k equal to 3 we have a class of graphs. What about k equal to 4? So, this is one question which people were trying for a long time, like over decades people were fighting over this, and still there is a fight going on. Is chi of g equal to omega of g, and then there is another possibility, omega g plus 1, right, or is it a function of omega of g, or is it any other value, okay. So, can you think of an upper bound? In the previous page we have given a lower bound, right, chi of g is greater than or equal to omega of g, right. What about the other end? Can I say I will require only these many colors, because one trivial is n. If n is the number of vertices, we will require at most n colors, right. Is there any other tighter bound I can think of? Maximum degree plus 1, right, that is where our click comes into picture, right. It could be delta plus 1. So, there is another option of chi of g being less than or equal to delta plus 1, right. So, what about this? Is it a tight bound? Chi of g less than or equal to delta plus 1 is what I had given already. So, now my question comes to this omega equal to 2 and chi equal to k. I know it is not a immediate step, okay. I will give you the answer, okay. In 1970s I guess, one researcher Mysileski, he gave a proof for this question. You give me omega, I mean a triangle free graph. When we say omega equal to 2, that means what? there is no triangles, at least no triangles. So, we forget about higher order complete graphs because there is no triangle itself. So, forget about higher order. So, a triangle free graph, in fact, he gave a collection of triangle free graphs whose chromatic number is k. Okay. For any k you give. So, this class is also called as Mycelinsky's graphs or collection. So, the proof goes very simple. He gave a constructive proof. So, starting from, I mean, inductively you can construct it, say for given any k. So, for k equal to 1, you will have just, you need only one vertex, right, or isolated vertices, and for k equal to 2, yes, an edge, right, and what about k equal to 3? Odd cycle, right. So, the odd cycle is our actual, what do we call? Say let me start with C5, that is going to be our base. So, the construction pattern goes this way. So, for any general k, okay, so we start the construction of for k using k minus 1, okay. So, for k equal to 3, we ended up in odd cycle, but the idea is you take a copy of G2. So, the labelings would be going this way. So, this is called as G1 and G2. So, to get G3, what you do is take G2. So, suppose G2 has p vertices, you add p plus 1 vertex more, okay. Say I call this as V1 and V2. So, let me add p plus 1 vertex, say 3 more vertices, which is denoted by U1, U2, and this special vertex will be called as Z, okay. So, the idea is you replicate for every vertex in the GK to construct the higher order graph. So, what you do is, since it is a replication, you join every vertex here. So, you take every vertex here and join it to all the vertices corresponding to VI's. Suppose I take a UI in the newly added vertex, I join UI to every neighbor of VI, okay. Similarly, here U2 is going to be adjacent to V1, right, and this new vertex Z is going to be added to the newly joined vertex. So, if you see, this is nothing but our C5 in, if I just redraw it. So, this is C5 and this is nothing but our G2, right, G3 I guess. So, now repeat the same process to construct G4, say for k equal to 4, I will go to the proof a little bit in a little while. So, take a copy of this C5, complete, sorry, 5 cycle on 5 vertex. So, add 5 more vertices to it and join them to the corresponding neighbors, okay. And add a super vertex to add to join edges between all these vertices, all these newly joined vertices. Right. So, if you see this newly constructed vertex, so let me also give you the labeling so you can get the feel for it. So, are you convinced that this is a graph which has no triangles? Why or how? This is a recursive construction, you can do this for any k, okay, just follow the same process and you can construct it for any k, okay. So, there are two questions that we need to answer in this, right. The first question is omega of gk is equal to 2 for any k that we are considering here. So, this is going to be our G4, right, and the chromatic number of gk is equal to k again. So, how do we prove this? Ultimately we need to prove it. It's just I cannot hand wavingly say and go away. So, how do we show that there is no triangle in the graph? Think of for any general graph, next level when you think about it, you have to give a proof for generic case. For 1, 2, 3, 4, 5 you can see it, visualize it. But when we go for higher order, we have to see why it is going to happen. So, there are actually multiple cases that you have to deal here. So, what we should do is we should give a say kind of an inductive proof. I know like my gk minus 1 is triangle free. Say suppose by induction I know 1, 2, 3 is triangle free. So, when I go to the next level, what I should be looking for? I should see where my triangle could be induced in this construction, right. So, where is the possibility? Obviously, I am not adding edges between gk minus 1. So, the copy of gk minus 1 is undisturbed. Similarly, to the edges newly joined those ui's, if you see, they are also not going to induce any triangles, right, because we are just adding them to the previous neighbors only, right. In place of vi, they are going to be ui, right. So, they will also not create any triangle. So, then what is the possibility? Passing through z is one possibility, right. So, if z is there, then what we should be looking at? Z is connected to ui uj, right, only two ui's. So, and we know ui's are not adjacent, they are going to be connected to vertices in the gk minus 1 level, right. So, that will not form a triangle. Hence, the first level is done. What about a vertex from ui and a vertex from vj's? Can they form a triangle? We have to look into all possibilities here, right. We know within vi's there is no triangle, that is what is the given condition we have come up from. Right. Suppose I look at a ui, suppose z is not a part of my triangle. Suppose there exists a triangle, z is not part of it, then it should come from ui's and vi's, right. So, that means what? The ui is going to be connected to it, the neighbors of vi, corresponding neighbors, right. If those two are going to be adjacent, the corresponding neighbors, then it would have meant that in my gk minus 1 itself there would have been a triangle, right. So, this creates a contradiction. So, therefore, there cannot be any triangle in our gk, right. So, now about the chromatic number, why do you require k colors, or do you really require k colors? Can I do it with less than that? Again go by induction, right. Suppose I know my gk minus 1 requires k minus 1 colors, right, because we have seen till k equal to 3, we know we require 3 colors, right. If I have to go to the next level, how do I color my ui's? Same vi, ui can take identical colors with I mean ui and vi could be identical. So, and z, if you see ui's are all already colored with k minus 1 colors. So, we need an extra color to color z. So, therefore, you require k colors, right, k minus 1 plus 1 more color you require. So, therefore, chi of gk is equal to k. Okay. So, this construction was actually named after Mysilewski and it is very famous, and this is the theorem what he proved, that there exist graphs with omega equal to 2 and chi of g equal to k. Okay. There exist triangle free graphs which can be colored using k colors for any k, given any k. Now, coming back to the part that you are all really interested to do, can you give me an algorithm to color a graph? What will be the best coloring algorithm that you can give? So, next we have to go into algorithm, right, we have to color them. Given k colors, how can I color a graph? Say suppose it is k colorable, okay. Then how do I color them using k colors?